This is lesson 10.3 about arcs and chords. There are several theorems in this lesson, and it's going to be easiest just to encapsulate them and most frequently as a picture or a diagram instead of the actual theorem. The first one you'll see here is theorem 10.2. We have two identical chords, and what you'll notice is that the arcs that they cut out of the circle happen to be identical as well. It works both ways. If you know that two arcs are congruent, then necessarily their chords are going to be congruent. Okay, just a quick definition here. We've actually seen these before in our chapter on area, but the technical terms here are inscribed and circumscribed. Whatever figure is on the outside, in this case the circle, is circumscribed, scribe meaning right and circum meaning around, and inscribed being the polygon, it's written on the inside. Okay, a second theorem. Again, it's just easiest to draw the picture. It's hard to communicate with words, or at least it's hard for me to get an idea of what the words are conveying. So I think the picture is a really good way to go. So you'll notice that we have a diameter, or sometimes we just have a radius that is perpendicular to a chord. When that happens, it cuts the chord in half, and it also cuts the arc in half every time. So if I have a problem like this, in the first case, I know something about the arcs. If this diameter cuts chord HK in half, or if it's perpendicular to it rather, then it bisects the chord. It also bisects the arc. And so if measure of arc HL is 53, then I know that the measure of arc KL is 53. Okay, I apologize that I can't write on this at this time. But if KL is 53, and they want to know MK, well, I know that ML is the diameter, so the measure of this semicircle is 180, and I'm going to subtract the 53 here. Leaves me with 127 degrees for this arc. In the same situation, we can use this theorem to find information out about segment lengths or chord lengths in addition to arc measures. I've already worked out this problem, but I'll take you back through it step by step. We need to find JL. JL, you might think to yourself at first, well, the radius is 10, so JL is half of that, but we don't know that it's half. What we do know is that our diameter is perpendicular to the chord, and therefore we have this right angle, and we know that we bisect the chord HK. So they tell us HK is 16, and therefore we know that JK is 8. Now I've added in, if you'll notice on the previous page, I didn't have this radius here. I drew that in because they told me the radius is 10, and when I do that I have a nice right triangle. If I know that the radius is 10 and this side is 8, I used the Pythagorean theorem to find the length of the side WJ, which was 6. And since WL is also a radius, its length is 10, I can subtract this 6, which leaves me with JL, which happens to be 4. Okay, and now our lesson on inscribed angles. This should not be a confusing term because we just met inscribed polygons. It's when you draw it on the inside. And so an angle that's inscribed in a circle is going to look very similar to an inscribed polygon, as opposed to a central angle, whose vertex is in the center, and thus central angle. The vertex is on the circle. It's inscribed in the circle, if you will. And we would say that it intercepts this arc. Okay. Again, another theorem that's going to be more easily understood if you just draw a real simple picture. Whereas the central angle and the arc are exactly the same, you can look at this picture and see that the inscribed angle is smaller than the central angle. And the example I have here is true in all cases. The inscribed angle is always exactly half of the arc that it intercepts, and also the central angle that intercepts that arc. Such as this, I strongly recommend that you write it down so you can write down the numbers yourselves, what they tell you, what you find out. They told me WX, which is this one right here, XY, which is this arc. Please forgive me for not having these arcs marked. UZ, which is 108, which is this arc right here on the bottom, and then they told me that UW and ZY are equal to each other. So initially I set them both equal to X because I didn't know what they were, and then I added up 20 plus 40 plus X plus 108 plus X, and I set that equal to 360, and I solved and found that each X is 96. So if you add up all the way around the circle, you'll find that there's 360 degrees, which is what we expect for a full circle. Once we've got that, we're ready to solve these interior angles. Now, angle 1 is an inscribed angle, just as we've learned about, because its vertex is on the circle. Because it intercepts arc UW, which has a measure of 96, it measures half that, which is 48. Angle 2 is another inscribed angle, vertex is on the circle, and it intercepts arc XY, which is a measure of 40, so it measures 20. Angle 3, it's a little bit wider, it intercepts arc UZ, which is 108 degrees, so it's half that, which is 54. I'm going to skip 4 for a second and go straight to 5, another inscribed angle. It also intercepts a 108 degree arc, so it's 54. And then finally, number 4, you might be tempted to say, well, it intercepts a 116 degree arc, and so it's half that. But I caution you, because angle 4 is not an inscribed angle. It's not a central angle either. It's just out in the middle somewhere. But what I do know is that angle 2, angle 3, and angle 4 make a triangle, and therefore, since these two add to 74 degrees, angle 4 has to be 106. Before we move on, I do want to point out angle 3 and angle 5 are identical to each other. They're both 54 because they intercept the same arc. And that's actually the subject of the next theorem. Okay, and I hope that again the diagram is clear enough for you. If I have two different inscribed angles, they're both inscribed because they're vertex on the circle, but they intercept the same arc, they have to be equal to each other. It's also true if they intercept different arcs, but the arcs are congruent. Okay, our last two theorems for these two lessons deal with inscribed polygons, particularly triangles. You'll notice the diameter is the long side of the triangle, and with quadrilaterals. You can copy down the theorem word for word if you like, but the picture here says it all. If you have a diameter and it's one side of a triangle that's inscribed in a circle, this has to be a 90-degree angle. That's pretty much all there is to it. So, for example, in this problem, we have two triangles that are inscribed in this circle. They tell us that VU and SU are congruent to each other. Find the measure of angle 2, okay, 1, 2, 3, and 4. Okay, well, you see that UT is a diameter, it goes to the center, and therefore I know that angle V is 90. Similarly, angle S is 90. They tell us that 2 and 4. Well, 2 and 4 have to add to 90 because all three of these angles add to 180. And since this guy is 90, 2 and 4 also add to 90. They are 3x plus 15, and therefore 3x is equal to 75, so x is 25. Okay, if x is 25, then angle 2 is 36 degrees, angle 4 is 56 degrees. Okay, and how do we figure out angle 1 and angle 3? Well, I do remind you that they told us segment VU and segment SU are congruent. Also, we know that these angles are congruent, S and V, and then this third side is congruent. Now, that tells us that we have an angle, side, and a side that are congruent, which we know is not one of our congruence theorems, but there is a hypotenuse leg theorem, which you may or may not have talked about in Chapter 7, which basically tells us these triangles are congruent. So therefore, angle 1 is equal to angle 2, and angle 3 is congruent to angle 4. Alright, one last example, and actually, by solving this example, we're going to figure out the final theorem. Quadrilateral QRST is inscribed in the circle, and they tell us angle Q to begin with, and angle R, and they want us to find angle S and T. Alright, well, the numbers that I've drawn in here are based on angle R. So I hope you can see that angle R is an inscribed angle, And since it's 102 degrees, the arc it intercepts, which is a very large major arc STQ, has to be twice that much. It's 204 degrees. And if this is 204 degrees, then this other arc has to be 360 minus 204, which is 156 degrees. So if arc QS is 156 degrees, the measure of angle T over here, which is an inscribed angle that intercepts it, has to be half that, which is 78. Similarly, since angle Q is 87, arc RT is twice that, 174, which means major arc RQT is 186, angle S is half that, which is 93. So what you should notice here is that opposite angles in an inscribed quadrilateral are supplementary. And that's exactly what our final theorem is. If you want to, I draw the picture here, and perhaps you can make up values for R and T. We could call R 105 degrees, and we could say that angle T here is 75 degrees. So you could look at that, hopefully, and see that they're supplementary.